First, we are going to discuss sequential pattern and sequential pattern mining, the concept. So the first thing is we should say sequential pattern mining is very useful, has very broad applications. One application could be in customer shopping sequences. For example, you get loyalty cards for your shops. You may want to see maybe one customer likely going to first buy a laptop, then a digital camera, then smartphone within 6 months. If this forms a pattern, you may be able to try to do some kind of advertisement to other similar customers, or serving some new incentive for this customer. Like a medical treatment from sequences, natural disaster like earthquake happening, it may have some sequences of natural and also human phenomena. Science engineering, a lot of things are processes. They evolve along with time. Similarly, stocks, markets, they have some kind of duration sequences. Weblog click streams, calling patterns for telephone and other things forming sequences. Even for software engineering, the programming execution form sequential patterns. The biological sequence is very, very useful for analysis, like DNA sequences, protein sequences. So we'll see trying to get sequential patterns out of those very big, vast applications could be very useful and important. Actually, we can distinguish transaction databases. Usually may not be important to look at their time effect. Sequence databases, they have timestamp attached with it. Time series databases, usually the time things happened actually is along the even or equivalent time intervals. Sometimes it's very consecutive. Then for sequential patterns, actually there are two kinds. One is gapped, another is non-gapped. The gapped pattern means you do allow to have gaps within those patterns. The non-gapped patterns means you will not allow these patterns. The sequence, everything is important. The consecutivity is important. If you have gap, you have to treat them very seriously. For example, for shopping transactions, probably you don't care customer in the middle buying some other things, so it's not important to study the gaps. Clickstream, sometimes you may say, some clickstream you may care about gaps, some you probably do not care about gaps that much. For biological sequences, in many cases you do care gaps. So the protein sequence or DNA sequences, if you insert many things in the middle of the two DNA sets, sometimes you may completely change the function. So let's look at the customer shopping sequence as a major example to study how to do sequential pattern mining. Sequential pattern mining essentially is you give me a set of sequences. The algorithm is trying to find the complete set of frequent subsequences satisfying certain minimum support threshold. Let's look at this example. We have a sequence database containing like 4 customer shopping sequences. Okay, what's the meaning of this? We look at this particular sequence. This sequence, the parenthesis means this one is within the same shopping basket. Then after that, you get another one, AB. That means this AB, following EF. But AB is getting together at the same time. Similarly, DF getting together but following AB. And then C, then B. Okay, that means each one of these you can think is an element. It may contain a set of items, or you call events. Then this one event may follow another one. The items within the event, the order is not important because they are in the same shopping basket. But for our convenience, we can sort them alphabetically. Then what is subsequence? Actually, any substrings within this one, you probably can see here, the subsequence, you may have a gap. For example, you say you can have A, you have BC. BC, actually, you chop this A. You can chop complete AC, then you get D. You can chop one F, you can get C. So this one is a subsequence of this longer sequence. Then sequential pattern mining. The sequential pattern essentially is, if you set a support, like a minimum support is 2, that means at least the 2 sequences contain these subsequences. You find those subsequences, this is a sequential pattern. For example, A, B getting together, then C. In this sequence database, this is a pattern of support 2. So sequential pattern mining algorithm is you try to develop algorithms which are efficient, scalable, and these algorithms should find a complete set of frequent subsequences, we call sequential patterns, and also should be able to incorporate various kinds of user-defined constraints. For sequential pattern mining, actually Apriori property, the property we have used in frequent pattern mining, still holds. For example, if we say a subsequence f sub 1 is infrequent, then any of its supersequence cannot be frequent. So that's almost the same idea as Apriori. So based on this idea, we actually can develop lots of algorithms. One representative algorithm called GSP, Generalized Sequential Pattern Mining, developed in 1996. Another one is a vertical format-based mining called SPADE, developed in year 2000. The third one we're going to introduce is pattern growth methods called PrefixSpan, developed in year 2001. And then we are going to study mining closed sequential patterns called CloSpan. Finally, we are going to discuss constraint-based sequential pattern mining. Now I'm going to introduce an interesting algorithm called GSP. It's Apriori-based sequential pattern mining method. This method is pretty simple. Okay. You start from a sequence database. Okay. Then you first try to get the singleton sequences, like the first one it appears. Okay. That means you scan database once, you count every single item it occurred in every sequence. Then you probably see A occur 3 times, B occur 5 times. So if you said minimum support is 2, likely G and H will be gone because their support is only 1. Okay. Then you find frequent length 1 subsequence A, B, C, D, E, F. With this, you can combine them as candidate subsequences. You may have AA, AB, AC, BA, BB, BC. Remember, AA is still important, means you first buy A, then buy another A. Then for the shopping basket, you may get AB together. That's why you may have AB as one event, one element, AC as another one element. You may get these kind of subsequences. In total, you will get 6 by 6, then you get 6 by 5 divided by 2, you'll get this number of candidate size 2 sequence. But without Apriori, without this pruning, you'll get much more. So even this minimal pruning still can reduce search space substantially. So in general, we can work out the algorithm like this. You put this one into a loop. At the very beginning, you can scan to find length k, which is length 1 frequent sequence. Then based on the Apriori, you can generate length 2 or length k plus 1 candidate sequence. Then you can go back to check and find the real frequent sequence. Then you go back to do the Apriori-based candidate generation. So generation test, you can go into the loop until no frequent sequence or no candidates can be found. So if you look at the execution sequence for this particular data set, you will find at the very beginning you get A, B, C, D, E, F, and G, H will be gone. They are painted in blue. So then you can, from here, you can go up to get frequent length 2 subsequences. Then you can generate length 3, length 4, length 5 until you cannot go along anymore. Okay. So this is the GSP algorithm. Now I'm going to introduce you another algorithm called SPADE, which is sequential pattern mining based on vertical data format. You probably still remember the vertical data format based frequent pattern mining algorithm called ECLAT. Here, for the same set of authors, they actually developed an interesting algorithm for sequential pattern mining. Okay. The idea is pretty simple. If you take the sequence, you do a little detailed study, you get a sequence ID, element ID, and set of items. So what you can see is for the first sequence, ID 1, element ID 1, you find item A, element ID 2, you find A, B, C, and so on. Okay. Then we can transform this into vertical format. That means we just look at where the A occurs and where the B occurs. So the A occurs, you probably can see, it happens in sequence 1, element ID 1, in sequence 1, element 2, and also sequence 1, element 3. So you get this one. The same, you can get sequence ID 2, 3, 4. Similarly, for B, you can find where the B comes is sequence 1, element 2. So you get 1, 2. Then how we can combine them into frequent sequence like A then B or B then A. If you say A then B, you will be requiring A is in front of B, or A's element ID is in front B's element ID. That means for the same sequence ID 1, if EID 1 is smaller than EID 2 of B, then you get one sequence EAB. Similarly, for B then A, what you get is this element ID of B should be smaller than element ID of A. For the same reason, you can get all of them for the length 2. Okay. So for length 3, what you need is you just get length 2 frequent ones. Then you do join. How do you do join? You probably can see this element ID, sequence ID should be the same. The element ID, this B share with this B, they are both 2. So you can join them together, you get 1, 2, 3 here. Then you join the other together, you can get a 1, 3, 4. Because element 2, you get A, you get a B, you can get A again. So to that extent, you actually can find all of them. Okay. So that's the reason you can use Apriori-based principle to find all the frequent subsequences. This algorithm was developed by Zaki in 2001, called SPADE, is sequential pattern discovery using equivalent class. We have introduced Apriori-based sequential pattern mining algorithm GSP. We have introduced vertical format-based sequential pattern mining SPADE. Now we come down to see pattern growth-based algorithm called PrefixSpan. PrefixSpan is a growth-based mining algorithm. Okay. To examine the sequential pattern in more detail, we need to introduce the concept of prefix and a suffix. The prefix means anything in the front, if it's frequent, you want to capture them as a frequent prefix, like A, B. Then their projection becomes a suffix. Remember, if you get AA, what you see is you got a position holder for the next one is B. So that's why we use underscore as a position holder. Okay. The similar thing, you get AB, the position holder will shift to C. So that means given a sequence, you will find a set of prefixes and a set of suffixes, or you can say prefix-based projection. Okay. Then for this projection, what we will find is first find length 1 sequential pattern. If they are frequent, we call them a length 1 sequential pattern. Then we can do divide and conquer. That means we divide the search space to mine each projected database. We have A projected database, B project database, C project database, up to F project database. This mining methodology called PrefixSpan or prefix projected sequential pattern mining. So let's examine a little detail. For this sequence database, if we find length 1 sequential pattern like this, then we can actually get length 2 sequential pattern by first doing projected database, then find length 2 sequential pattern. That means if they are frequent in this projected database, they will form length 2 sequential pattern. And then we can do length 2 sequential pattern based projection, find AA project database, AF project database. Okay. Then we can keep this one ongoing. Okay. The major strength or advantage is there's no candidate subsequence to be generated, and the projected database keeps shrinking. So let's look at some implementation tricks. So if you do the projection, like you're really taking the sequence to do projection on A, projection on AB, you will get largely redundant subsequence, or you say postfix, but they are largely redundant with the original string. However, we do not need to do the real physical projection. What we need is we call pseudo projection. That means you just say, what is A's projected database? It's the same sequence, but the position is number 2. What is AB's project database? Is the same sequence on S, but the position is number 4. So if you register the next position to be scanned, you essentially register the projected sequence or suffix. Okay. So if the database can be held in the main memory, this pseudo projection is very effective because there is no physical copying or suffix. You only need pointer to the sequence. You just get offset, you get suffix. But if it does not fit in the memory, you use pointer, you may involve lots of disk accesses. So you may really want to do physical projection because once you project it, quickly this set can be fit in the main memory. That means we can integrate physical and pseudo projection. Anytime when the data fits in the main memory, you can use pseudo projection. Now we study another interesting issue called mining closed sequential patterns. The algorithm mining this is called CloSpan. So what is closed sequential patterns? Similar to closed frequent item sets. The closed sequential pattern S means if there exists no superpattern S prime, and this S prime and S have the same support, then S is a closed sequential pattern. In another word, closed pattern means for the same support, you will find the longest one. That's the closed pattern. The other ones probably does not really matter. Okay. For example, let's look at this example. Suppose we find 3 sequences, ABC with support 20, ABCD with support 20, and ABCDE with support 15. Which ones are closed? ABCD is closed in the sense for support 20, ABCD is the longest one. Okay. Then ABCDE is also closed because the support is 15. There's no longer one than 15, which is a super sequence of ABCDE. So there are 2 ways to mine closed sequential patterns. One way is you first mine all the sequential patterns, then you find which one is closed, like this ABC. You can knock it down, then you get a set of closed sequential patterns. But this is not very efficient. Okay. What we want is directly mine closed sequential patterns. This will reduce the number of redundant patterns to be generated in the middle, but it will attain the same expressive power because it's a lossless compression. So there's one interesting property like this. I mean, if S is a superset of S1, S is closed if and only if 2 projected databases have the same size. Let's look at this. For example, for this sequence database, if you find F, the project database, and Another sequence is AF. This is the project database. If these project databases have exactly same size, then this actually means AF is closed. Essentially, you only need to mine one. That means you can merge them. Okay, so you will be able to develop two kinds of pruning. One called backward subpattern pruning. Okay, this is a subpattern, you can prune it. Another is backward super pattern pruning. So you probably see you can use super pattern to chop up the subpattern. You'll get into this. Okay, so with this spirit, we can develop an efficient algorithm called CloSpan. It greatly enhances the processing efficiency. I'm not going to discuss very detail. For details, you can read this paper. It gives you all the detail on the CloSpan.